Okay, so if you've been following this playlist, I've been doing a lot of videos on getting equations of motion for different systems, and now what I'm going to do is solve them using classical differential equation techniques. So the first example I did was a car moving in 1D space, so it could only move forward and back. And we were looking at the velocity dynamics with a thrust input, and the thrust basically essentially being that the tire is moving forward, and then there was a drag term. And so it was V dot plus B over M. V equals my thrust input, okay? And so what I'm going to do is I'm going to assume that I need a couple things to solve this problem. First, I need the initial conditions. So I'm going to say that the initial velocity is 0 meters per second. And then I'm going to say that the thrust is a constant, and I'm going to make it T naught. So this is a constant force in newtons. Okay? All right, so now I have everything that I need to solve this problem. So the way I solve these problems is I break it up into a homogeneous and particular solution. So the homogeneous solution is where you, homogeneous solution is where you set the left-hand side, and it's not really the left-hand side, you take everything with V in it, or everything with the state variable in it, and move it to the left-hand side. And then everything on the right, you set to 0. Another way you can look at it is you set the forcing function to 0. You also have to consider, right, what are we looking at here? We have thrust as our input, G is our plant, this is the car, and V is our output. So the homogeneous solution is where you set the input to 0. That's another way to look at it, where you set all of the forces to 0. Okay? So with a homogeneous solution here, what you do is you assume a solution. So typically what I do is I say VH, H is homogeneous, and I say AE to the ST. And so this is like a guess. Now, I know this is right because I've done this problem before, but typically all differential equations are solved this way, where you assume sort of an exponential function here. I've got one derivative in here, so this is a first order example. So if I take a derivative of the homogeneous solution, I get AS e to the ST, okay? And then what I do there is I plug both of these back into the equation above. Remember, B is drag and M is mass, but both of those are constants, okay? A is also a constant, S is a constant, T is time. Cool? All right. So I'm going to plug this in. So I'm going to get AS e to the ST plus B over M A e to the ST equals 0. And if you look at there, I got some like terms and things like that, so I'm going to factor some things out. I'm going to get A e to the ST, S plus B over M equals 0. Now if you look at this, if you've done differential equations before, you'll see a couple things that look familiar. First of all, I have these three terms here that are multiplied by each other. If you remember from algebra, I guess, if you have different things multiplied by each other by equals 0, you actually have three solutions. The first solution is that A equals 0. Now, if A equals 0, it means that the homogeneous solution equals 0, and unfortunately, that does satisfy my V naught equals 0, but later on you'll see that it doesn't satisfy my total solution. What you'll end up getting, if you look at this here, if V homogeneous is 0, if you plug in 0 plus 0, that doesn't equal T naught because you have a constant force. This is saying that the velocity is always 0 for all time, which is not true because I'm applying a force. I would imagine that the car would speed up, so this isn't going to work. The second solution is that e to the st equals 0, but this isn't possible. If you look at, let's see, time and e to the st, you're going to get something that looks like this. Excuse me. You're going to get something that looks like this, but it's never going to get 0, so this is impossible. So the only other option is for s plus b over m to equal 0. Now this is a very, very special equation. It has a name. It is the characteristic equation, okay? And it basically defines the dynamics of the system, okay? Now what you do, this is actually a valid solution. What you get is that s equals negative b over m. And these are typically called the roots of your car poly, your characteristic polynomial. And and it's also called, your poles of your system. And poles will make sense later on in the semester, but for now, we're just going to call them that, roots of the characteristic polynomial. So what you end up getting is that VH of t is a e to the negative b over mt. Cool? So we can sort of box that and save that for later. So now what we want to do, we already have a homogeneous solution. So now what we do is we find the particular solution. So the particular solution goes like this. Particular. T is my forcing function, and it is a constant. So my guess, v particular of t, is I'm just going to pick a constant. Since the forcing function is a constant, my guess is a constant. Well, the derivative of vp of t is 0, and so if I plug that into the equation, now I'm doing the particular solution, I need to use the left-hand side. I'm going to get 0 plus b over m equals t naught, and now you need to look, the 0 goes away. What is unknown? I know the force that I'm applying, so that's known. I know the mass of my car. I know the drag coefficient. B is the only thing I don't know, so I need to solve for B. So in this case, B is equal to T naught M over B. Okay, and I'm going to box that and leave that there. So now what you do is you use the principle of superposition. Use the superposition principle. And the superposition principle says that V of T is equal to V particular of T plus V homogeneous of T. And the reason why this is okay is because the V homogeneous of T satisfies this equation, which is 0, and this equation satisfies the particular solution, which is equal to T naught. So you end up getting a solution that equals 0 plus a solution that equals T naught, and then both 0 plus T naught is T naught, which all adds up together to get T naught on the right-hand side. So my total T then is my homogeneous solution, which is here, a e to the negative b over mt plus T naught m over b. And now you need to look at your solution here and say, what is unknown? What don't I know? Well, I don't know A. So now what you need to do is you need to plug in your initial conditions, okay? So you plug in your initial condition there and you get V of 0 is A e to the 0, like, so that's time, e to the 0 is 1, so you get A plus, and I'm going to just replace this with B, and what you get is that A has to equal negative B. And there you go. So what I'm going to do is I'm going to erase this here because that's kind of irrelevant, and I'm going to write the total solution up here. Okay. And so my total solution, if you look at this, if A equals negative B, that's negative B. I can factor B out on the left, and so V total of T is T naught M over B times 1 minus e to the negative b over mt. And that, my friends, is the total solution, okay? So now we can take a look at this and see what happens. We can actually draw this, all right? So let's draw this on time and v. So what happens when t is equal to 0? Well, if you plug in 0, you're going to get e to the 0 is 1, 1 minus 1 is 0, okay? If you plug in t equals infinity, what happens to infinity? Well, at infinity, this is 0, so you're going to get T naught M over B, and that's going to be an asymptote. You're never going to quite get there. This is an exponential, so the graph looks like this. Okay, and that makes sense. If you put the gas pedal, sorry, let me use my right foot. If you push the gas pedal to a specific spot and apply a constant force to a vehicle, eventually the drag will catch up, all right, and the force from your car will equal friction and drag and all those things, and your car will stop accelerating, and you'll reach a final velocity. If the... Did I do something wrong? This says here, if the mass increases, M over B, if the mass increases, I'm going to go faster? Oh, okay, that makes sense. Oh no! You guys, I forgot to divide by n there. Okay, what does that change? Homogeneous solution is the same. Let's see. Particular solution turns into this. N's cancel. Okay. and then that means down here the m cancels. A is still equal to negative b, the m cancels, and the m cancels. Okay, now we're in business. So now what does this say? So this says that if I apply more force, I will go faster. If I have more drag, I will slow down. According to this equation, mass doesn't matter. Slow down. Mass matters. It matters how long it takes for you to accelerate, because that affects this term here. And so if you increase mass, it will take longer for you to get to your final velocity. Not to mention, we're only modeling drag. If you increase mass, you're going to have more friction, and that's not something that we've modeled here. So if you are a hockey puck on ice, and there's like almost zero friction, or if you're in space and there's drag, I don't know. If you're neglecting friction, this is what's going to happen. If you apply more force, you'll go faster. If you have more drag, you'll slow down. In this case, mass doesn't matter. If we modeled friction, then that term would have been in there. Okay, so this is how you do the solution to a first order system. I'm not going to do the differential equation solution to a second order system, because it's basically exactly the same way. You assume a homogeneous solution, you take a derivative, except for second order systems, you take two derivatives, you plug it in, and you'll get a characteristic equation. And instead of getting one root or one pole, you'll have two poles. And so your homogeneous solution will have two terms. I'm going to go over second order systems in excruciating detail in a different chapter. And so for here, I'm just going to show you first order systems here. So hopefully this helped, and hopefully this cleared some things up with solving these problems. I personally don't like solving problems this way. I show this at the beginning of the semester just to kind of say, this is how you could solve differential equations in controls, but we're not going to do that. We're going to use Laplace transforms, and I'll show you in other videos how to do Laplace transforms and get transfer functions, and they are way better at solving these types of problems. But if you are here doing differential equations and you want to learn how to solve a first order system, here you go. Hope this helped. Have a good night.